Welcome to the Displaying Data of Two Events revision session. This will be looking at how we can display the outcomes of two events in different ways. This might be from a simple list to sample space diagrams and then finally to tree diagrams. So, listing the outcomes of two events. When two or more events occur, e.g. rolling a die twice or playing two matches of football, then it's possible to write the outcomes of the long list of the different possibilities of what could occur. Remember that each outcome of the first event can occur with each of the outcomes of the second event, unless you are specifically told in the question that they can't. So the question will often provide you spaces for your answer, and say you do not have to fill all the spaces divided. This is a big hint to you. Normally this means there will be spare spaces, so don't be tempted just to fill things in because you think you should. Once you've written your own list, you should check your final answers to ensure you have not duplicated any answers. If you do, you will lose marks. It's best to do the list in sequence, with the first outcome of the first event occurring with each of the outcomes of the second event, before then moving on to the second outcome of the first event with each outcome of the second event, and so on and so on. So you should be able to do this, so let's have a practice of skills. Here we have a menu. I need you to choose one start from one main and list all the possible combinations that you could get of those. So pause the video and do that now. So what should we have got? Well, you should have had soup with chicken, soup with beef, soup with pizza. Then you could have prawn cocktail with chicken, prawn cocktail with beef, prawn cocktail with pizza. Or finally, you could have had melon and chicken, melon and beef, and melon and pizza. We've been very ordered in the way we've done it. We've done the first outcome of the starters with each main, then the second outcome of the starters with each main, and then the final outcome of the starters with each of the mains. We've got no repeats. There are 9, there are 3 starters, 3 mains. There will be 9 outcomes in total. However, sometimes the number of different outcomes are very large and a list will just become too hard to keep track of. When this is the case, it's easier to actually create a two-way table to show the outcomes, and this is known as a sample space diagram. The outcomes of the first event are normally shown going downwards in the table in the first column, while the outcomes of the second event are displayed across the table in the first row. You then fill in the areas underneath and to the side of each of these outcomes to show what the outcomes of both events are. Often, sample space diagram will be partially filled in and you will be asked to fill in the gaps. Be sure to check how the final outcomes are being generated for each example. If you have 2 dice, are you just simply writing down what is occurring on each dice? Is it 1, 1, 2, 2, 6, 3? Or do you need to do something with each number, e.g. add them together to get a total? Or you could be a subtract or a multiply. Make sure you read the question to check what they want you to do. So here's an example of a sample space diagram for the rolling of 2 dice and where we add the numbers of each dice together to get the final total. So the first dice, 1 to 6, has been written down in the first column. The second dice, 1 to 6, has been written across the top in the first row. We then have a 1 on the first dice, 1 on the second dice will get us a 2, which is in the top left. You might then get a 4 on the first dice, a 3 on the second dice, and if you go across from 4 and down from 3, you'll get 7, because 4 add 3 is 7. And quite often, as we said, most of this will be filled in and you'll have to fill in a few blanks to get the correct. Always good to look for patterns. You can see these patterns are getting bigger as we go along. You got 2 to 7 across in the second row down, 3 to 8, 4 to 9, and so on and so on. So as you move left to right, the numbers get bigger, and as you go from top to bottom, the numbers get bigger by 1 as well. Now, why is it useful? Well, it's possible to generate probabilities of outcomes for a sample space diagram, but only if all the outcomes depicted on the sample space diagram have the same probability of occurring. If that's true, then the probability of an event occurring is written as a fraction with the number of times that event occurs on the top of the fraction and the total number of different outcomes in the whole sample space diagram on the bottom. So we go back to our example. If I'm looking at what's the probability of rolling a 6, then the P of 6, P of getting a 6, is going to be the number of times I could get a 6. Well, I could get a 1 and a 5, I could get a 2 and a 4, I could get a 3 and a 3, I could get a 4 and a 2, and I could get a 5 and a 1. There are 5 ways of getting a 6 in this sample space diagram. So 5 goes on the top of the probability, and in total there are 36 6 by 6 different outcomes, so 36 different outcomes on the bottom. So the probability of getting a 6 from this would be 5 out of 36. Now, always check, can I cancel that fraction down, make it simpler? And I can't, because nothing divides into 5 and 36. So let's practice those skills. What I wish you to do is copy and complete the sample space diagram, then calculate what's the probability of getting a 4 for this sample space diagram. So pause the video and do that now. Okay, so here's the completed sample space diagram in black. I could have got a 1 and a 3, which would have given me a 4. I could have got a 2 and a 1, which is 3, 2 and a 2, 4, 2 and a 3, 5. Or I could have got a 4 and a 1, 5, 4 and 2, 6, and 4 and 3, 7. You then got asked to work out the probability of getting 4. Well, the probability of getting 4 will be the number of ways you get 4, which is twice. So I could get a 1 and a 3 or a 2 and a 2, over the total number of outcomes possible, of which there are 9. 3 by 3 is 9, so the probability of getting a 4 is 2 out of 9, which again doesn't cancel down and become simpler. Now, often events do not have equal probabilities of occurring, and therefore a sample space diagram wouldn't be much use to us. So a different way of showing the outcome of 2 or more events, while also showing the probabilities that are occurring, is tree diagrams. These are written as a series of lines which are branches which project out to the right from a single point, with each outcome having its own branch. So if you were having a flip of a coin, you could get heads or a tail, so you'd have 2 branches. If you roll a die, there are 6 different outcomes, you'd need 6 branches. So the number of branches is determined by how many outcomes there are. So the outcomes are written on the end of each branch. So when you get to the end of the branch, you write what would occur, while the probabilities of that event actually occurring is written on the actual branch itself in the center. Subsequent events are then drawn as a further series of branching lines from each of the outcomes of the previous. So if I rolled head the first time and I flipped the coin again, I would have 2 branches coming out of head, which would be one with head and tail. Here's an example to show that a bit easier. Here I'm picking a ball from a bag. In total there are 5 balls inside the bag. 2 of the balls are red and the other 3 are blue. So I've only actually got 2 different outcomes for picking a ball out of the bag. I pick a ball out, I know it's coloured down, I put it back in. I could have got a red, and the chance of getting a red would be 2 out of 5. So red is written at the end of the first branch. And on the branch, I write the probability, which is 2 out of 5. 2 reds out of 5 balls. However, I could have got blue ball the first time. So at the end of the other branch, coming up and downwards this time, I would write blue. And the chance of getting a blue is 3 out of 5. 3 blues out of 5 balls. So I'd write 3 5s on that branch. Now, because I've got the ball back in, and I take another ball, the probabilities of getting red and blue remain the same. So if I got a red first, I would draw 2 branches coming off from where I've written red, and at the end of those I would write red or blue. And on the branch which is going to the red, I would write 2/5 because I've got 2/5 chance of getting a red. And on the blue branch I would write 3/5 because I've got 3/5 of getting a blue. Now of course I might have got a blue the first time. So again, the second time after getting a blue, I've got 2 different ball colours I could get. I could get a red or a blue, so I've got 2 branches coming off again. And we know the probability of getting a red is 2 out of 5, and the probability of getting blue is 3 out of 5. So there are actually 4 different outcomes I could get, which I've written on the end after the tree diagram, which is I could have got a red and then a red, I could have got a red and then a blue, I could have got a blue and then a red, or I could have got a blue and a blue. Now, things to notice. Look at the branches which come together here. The red and the blues are coming together, and you've got 2 fifths and 3 fifths. Now, if I add the 2 fifths and the 3 fifths together, I get 1. Now, that's not a mistake. Every single time you add together the probabilities of branches that join together, they will add up to 1. Why? Because 1 means they're certain to happen. So when you pick a ball, you're certain to get either a red or a blue, because they're the only colours you can get. And that's what this says here. Note the probabilities of branches that meet together sum to 1. This is always true of all tree diagrams and all branches that meet. Now, we can use this tree diagram then to calculate probabilities of different events occurring. For example, what is the probability of picking 2 blue balls in this case? Well, the chance of getting 2 blues will be I've got a blue and then a blue, which is the bottom of these branches. So what's my chance of getting the first blue? 3 out of 5. What's the chance of getting the second blue? 3 out of 5. Now, interesting, as you move across a tree diagram, and you can see with the little arrow I've drawn on, we multiply probabilities. So as you move across, you're going to multiply probabilities. So the probability of getting blue and then a blue will be 3 fifths for the first blue, multiplied by 3 fifths for the second blue. So in total, the probability of getting a blue and a blue is 9 out of 25. And again, that doesn't cancel down. In addition, there may be multiple pathways which give you the desired outcome. We just had blue. There's only one way you can get a blue and a blue. However, what if I wanted to get 1 red and 1 blue? Well, I could either get red followed by a blue, or I could get a blue followed by a red. So in this case, I have to do a couple of calculations. First, you have to multiply the probabilities as you move across. So red multiplied by blue will be 2 fifths multiplied by 3 fifths, while blue and then red will be 3 fifths multiplied by 2 fifths. So once you've got those probabilities at the end, you then add those probabilities together to get the final answer. So multiply as you go across probability tree diagrams, and then you add the probabilities as you go down at the end. So in this case, probability of getting 1 red and 1 blue is probability of getting red and blue, add the probability of blue and red. So probability of getting red and blue would be 2 fifths multiplied by 3 fifths, which is 6 25ths. Add the probability of blue and then red will be 3 fifths multiplied by 2 fifths, which again would be 6 out of 25. So in total, 6 25ths add 6 25ths. The chance of getting one of each colour is 12 out of 25. Again, that does not cancel down. So let's practice those skills. Here we've got a situation where James has gone to an arcade. He is playing first the teddy grabber one time, and then he's playing one go on the penny drop. The probability that he wins on the teddy grabber is 0.2, which has been placed on the tree diagram for you, while the probability that he wins on the penny drop is 0.3, which again has been marked once on the diagram for you. So the first thing they want you to do is complete the tree diagram. And finally, they want you to work out the probability that James wins on both the teddy grabber and also on the penny drop. To do that, now pausing the video. So here's the answer. If you've got a 0.2 chance of winning for the teddy grabber, when we know the branch is going to add up to 1, 1 subtract 0.2 is 0.8. The chance of losing on the teddy grabber will be 0.8. If you move on to the penny drop, the chance of you winning the penny drop was 0.3. So therefore, win and loss are joining together, so those two branches are going to add up to 1. 1 subtract 0.3 is 0.7. Now, The chance of you winning on the penny drop is not dependent on whether you win the teddy grabber or not. So therefore the probabilities remain the same. You've always got a 0.3 chance of winning the penny drop and 0.7 chance of losing. So we fill those in on the bottom tree branches as well. So next question was, what is the chance that you win on the teddy grabber and he also wins on the penny drop? Well, in that case, win and wing will be going across the top branch and then the top branch. So we've got 0.2 and 0.3, and we know as we move across those branches, we multiply. So we're going to have 0.2 multiplied by 0.3. You've only got a 0.06 chance of winning. If they give you decimals in the question, you use decimals as your answer. So finally, moving on to the last bit for today's revision, is tree diagrams when you are not replacing the event. This will have a direct effect upon the probability of subsequent events. So if you were to take a sweet from a pack and you eat that sweet, the next time you went to the same pack, the chance of you getting a different sweet will now have a different probability. Why? Because there are now less sweets in the bag, and there are less of the type of sweet you ate the first time. So that would affect the probability of you getting the same type of sweet. So normally when you're doing non-replacement, the denominator will always decrease by 1, because if you take one thing out and don't replace it, your denominator, what you're choosing from, will always go down. Now, only some of the numerators will go down, some will not change when you do this, but the denominator will always get 1 smaller at least when you are doing non-replacement tree diagrams. So here's a good example. Here was again picking balls out of a bag, but this time we've got 10 balls. 4 of the balls are red and 6 of them are blue. So that gives me a 4 in 10 chance of getting a red ball. So if I take a red ball first, what's the chance of getting a red ball the second time? Well, this time, if I've removed the red, instead of having 4 red balls left, I've now only got 3 red balls. So 3 will be on the top. However, if I remove a red ball, I've also now reduced the overall number of balls from 10 to 9. So the chance of being red will be 3 out of 9. Of course, we now know that where 2 branches join together, so that second pick, top red and blue, if red is 3 out of 9, that must make the blue 6 out of 9, because 3 9s and 6 9s will give you 1 whole one. Moving on to this lower branch, if you've got a 4 in 10 chance of red, you've got a 6 out of 10 chance of blue. Now, red here, well, I haven't removed a red, so I've still got all 4 reds left in on the second pick. So my chance of getting red this time is 4 out of 9. It's higher for the reds here in this case. However, if you try to take another blue, the number of blues would have reduced because you had 6 and you removed 1. So you've now got 5 blues out of the 9 remaining balls. So we end up with 4 tenths and 6 tenths for the first pick. Of course, they add up to 1. Now, if you pick red the first pick, you would get red and blue with 3 ninths and 6 ninths. So you add those together again, you get 1. Or if you got blue the first time, chance of you getting red is 4 ninths, while 5 ninths of blue. If you were then going to use this, okay, you can use the basic rules. They stay the same. As you move across, you're going to multiply probabilities. As you move down, you're going to add the probabilities. So let's practice those skills finally. Fiona's got a box of chocolates. The box contains 11 caramel chocolates and 9 plain chocolates. She is going to pick 2 chocolates at random and she's not replacing them back in. She's going to eat them or give them away. She hasn't got many more. So first you need to complete the probability tree diagram. They've given you the outcomes. You're going to have to write on the probabilities. Remember, the probabilities will change because you are not replacing the sweet. They're not putting the chocolate back in. And then I want you to work out probability that Fiona picks 2 plain chocolates for her picks. So pause the video and have 5 seconds, time to go and do that. Let's run through the answers. If you chose a caramel first, with the first pick, you would have had 11 caramels out of 20, so the probability was 11 out of 20. So if you removed a caramel the second time to get a caramel, there would only be 10 caramels left, and there would only be 20 sweets because you removed one of the sweets, so it would be 10 out of 19 for the caramel the second time. Now you would still have all 9 plain chocolates left, so the branch below would be 9 out of 19. And what do we know? Well, 10 out of 19 add 9 out of 19 adds to 1, so we know we've got that right because our probabilities are always going to add up to 1. Now, you might not have eaten a caramel the first time. You might have got a plain chocolate. Now, there were 9 plain chocolates, so 9 out of 20 is the chance of you getting a plain chocolate the first pick. You could then go on and get another plain. If you remove a plain, you've only got 8 plains left, and in total 19 chocolates. So there'll be 8 out of 19 to get a plain the second time if you had the plain the first. However, you still have got all 11 caramels left, so the chance of getting a caramel the second time would be 11 out of 19. So notice 11 out of 20 had 9 out of 20 for the first pick, gives me 1 whole 1. The top branches converging for the second pick is 10 out of 19 at 9 out of 19, which is 19 out of 19, while the lower branches 11 out of 19 at 8 out of 19 is still 19 out of 19. So how do we work out the probability that Fiona picks 2 plain chocolates? Well, she got a plain for the first one, 9 out of 20. You got a plain for the second one, 8 out of 19. And we know as we move across a tree diagram, we multiply. So the probability of getting a plain and then a plain will be 9/20ths multiplied by 8/19ths, which is 72 over 380, which cancels down to 18 out of 95. Thank you.